So this is a question from the PAT 2022 exam. You can immediately see that it's a couple paragraphs, there's an equation, a bunch of percentages. It's clearly going to be an involved question requiring a reasonable amount of interpretation and careful reading. If you haven't already looked at the ESAT video from earlier, I'd recommend that. That is the style of a lot of the PAT. The earlier half, I'd say, of the PAT exam is these kind of, dare I say, warm-up questions, easier style, faster pace, whereas the tail end of the PAT exam is questions like these, harder, slower, more complex. I'll give you a moment now to attempt this question for yourself, see how it goes. With a complicated question like this, I often like to start at the end. That can often provide clarity as to where we're going and therefore how do we get there. So ultimately, our goal here is to provide a time. What time? In minutes. And that's going to be the beta particle emission rates are equal. That's what makes that time special. Okay, so perhaps we just start with, let's say we've got some emission rate EA, and that's going to be equal to the emission rate B. Cool. So that's what we're aiming for. Now they've told us the total particle emission rate here, and they've told us that only a portion of that will be the beta particles. So actually immediately here, we can write down the equation that we know we're going to use to solve this problem. So if I plug in this for our emission rates, we have lambda A in A of t, which I'll use this equation up here. So this is going to be NA 0 e to the minus lambda A t. And of course, we only want 64% of this. So times 64 over 100, because only part of that will be beta particles. And this is simply going to be equal to the emission rate, beta emission rate of substance B. So we copy this exact thing. However, this time 44% of the decays are beta particles. So having the clarity and calmness to figure out, what do I want? This thing. Where is the question giving me that? This thing. I'm not trying to rush into any quick calculations or speed things. I'm just trying to give myself some space and some perspective here on exactly what we're trying to achieve. And I think now that we've got this equation, already life is going to become a lot easier. We're told these two things are the same. Fantastic. So we can cancel these two. Brilliant. And now we've got an equation where we've got a time t. Fantastic. That's what we want to solve for. And just lambda A and lambda B. A strong recommendation I have for the PAT is do a lot of extension physics problems while you're in high school, while you're preparing for it. So the Senior Physics Challenge, SPC, the Physics Olympiad, BPHO, these are really good resources for extending you just a little bit beyond high school level. So that problems like this, you've actually likely come across this before. I mean, this equation is fundamental to the entire topic of radioactivity. This isn't some niche formula that pulled out from a book. This is the natural next step in your physics understanding of a topic that you've come across in high school. If you've done some of these competitions, even something like Isaac Science, just an online resource that you can use that helps to teach you a lot of these things, you will be able to, in all likelihood, shortcut this next step that we're about to do, which is figure out what actually lambda A and lambda B are. So this has to do with the half-life, which is the only piece of information in the question actually that we've yet to use. We've got a 1 hour half-life and a 15-minute half-life. What actually is the half-life? Well, I'm sure you could tell me that it's the amount of time taken for the substance to halve how much of it there is. Given the only time dependency is in this term, maybe you can believe me if I say that e to the minus lambda t, when that is the half-life, is going to be equal to a half. That's when we have half as much. We have half of N0 stuff left. Now, if you take some logs, do a little bit of algebra here, you will see that lambda is equal to ln2 divided by the half-life. This is a very standard result. So if you didn't know, now you know, and we're in a position to use this. Fantastic. So if we actually specifically check here, lambda A, for example, and lambda B, we can now write these down. Now our answer is going to be in minutes. So if we plug in the half-life times in hours and solve this big equation down here, we get a time in hours. If we plug in a half-life in minutes, the time answer will be in minutes. So both work. Hours is probably slightly simpler maths, but we have to do a unit conversion at the end. I'm going to use minutes from the outset just because I think it reduces the amount of errors I can make if I get my units fixed from the beginning. So lambda A is going to be ln2 divided by 1 hour, so that's 60 minutes, and lambda B is going to be ln2 divided by 15 minutes. Fantastic. And now it's just a matter of plugging these into the equation and solving it. So let's have a look at what that actually entails. So ln2 divided by 60 times e to the minus ln2 times t over 60 times, now I'm already going to cancel these hundreds just to get one step ahead of ourselves. And ln2 over 15 e to the minus, same deal, ln2 times t over 15 times 44. Brilliant. So to solve this, I think maybe getting all the exponentials on one side and everything else on the other side is useful. We can certainly cancel these logs. So we're going to get 64 times 15 divided by 60 times 44 equals, now this is going to be e to the ln t, sorry, got to be careful here, don't we? Ln 2, so this becomes positive, and then if we're multiplying by the other one, I'm actually going to write this in line here, ln 2 times t divided by 15, because this is going to let us take logs of the whole thing. So it's ln of this whole thing here equals this whole thing here. So I'm going to cheat because I copy and paste. Voila, makes my life easier. Fantastic. Cool. And then from here we can continue solving, can't we? Just some couple more reasonably standard algebraic steps. So here, for example, ln2t, we can probably factorize out. So this whole bracket here, I'm cheating because I've done this question in advance. I know that's actually just ln of 4/11. That's how that simplifies down. Equals ln2 times t times 1 over 60, 1 over 6t minus 1 over 15. Oh, my brain just did an auto cue. That's interesting. And yeah, t equals ln 4/11 divided by ln 2 times 1 over 60 minus 1 over 15, which we can use our PET digital calculator to solve. And I believe this is 29 minutes or something. 29-ish minutes. So let's review. How much actual maths do we do here? We wrote down this equation, which was the equation they asked us about. We substituted in a few values. We did about 4 algebraic steps. This whole thing, I think on average for these papers, we usually have about 1.5 minutes per mark. So 5 marks would correspond to 7.5 minutes. But usually I'd say these later questions tend to be slower than the earlier ones. So if you can zip through some of the earlier questions, you'll have maybe 8-9 minutes to do a question like this, which at first will be hard. But with enough training, I think that, and again, we're aiming for 80%, not 100%, it can become much more reasonable, much more